Okay, well, let me start by also from Paris wishing a happy new year to everybody. May it be healthy and prosperous and hopefully more peaceful. And then let me thank the organizers for giving me the opportunity of starting 2024 in this lecture series with a talk on Horn's exchange in electrochemistry, electronic properties of real-life battery materials from a dynamical mean field perspective. A short disclaimer is in order because I'm neither a chemist nor a battery materials expert, despite of what I'm going to pretend during the next half an hour. This is work mainly done by my former postdoc, Jihan Sim, who's really the hero of what is going to come, and in collaboration with Didi Sharma and Jean-Marie Tarascon. Whoops, and now I cannot move on. Ah, yes. So batteries, battery compounds probably do not need much of an introduction. We have witnessed the revolution in mobile electronics, enabling us nowadays to run around with our mobile phones or portable electronics more generally. We are witnessing the electric vehicle revolution, which is starting. And we are probably all putting high promises in the advances in battery technology for making use of renewable energy, such as solar power or wind power for the energy transition. The history of batteries goes long back, actually, as you probably know, to Volta, who put together the first Volta cell, just a pile of zinc and copper plates in sulfuric acid electrolyte, and then the oxidation of zinc and the reduction of hydrogen in the sulfuric acid gives a voltage that you can use at the ends here. However, the problem of this kind of technology was, of course, that this is not rechargeable. This is already different for the good old lead acid battery, where you have lead being oxidized and lead oxide being reduced in the presence of sulfuric acid again to lead sulfide. This is now rechargeable, but had serious drawbacks due to the use of sulfuric acid and, of course, also limited energy density, you know, the good old car batteries of a certain volume. The development of the lithium-ion battery was honored by the Nobel Prize in Chemistry in 2019. And in particular, were highlighted three important discoveries related to that. The first one was due to Stanley Whittingham, who showed reversible lithium insertion into inorganic compounds, into, in particular, layered compounds such as titanium disulfide, and then also later molybdenum disulfide or selenides. So compounds that nowadays we would call famously the transition metal dichalcogenides. The cathode material was revolutionized by John Goodenough, who introduced the lithium cobalt oxide as cathode material. However, the true commercialization of the lithium-ion battery at that stage was still hampered by the use of metallic lithium as the anode, and that posed serious security issues due to dendrite formation, which could be solved when Yoshino in Japan, Akira Yoshino, the third Nobel Prize winner, actually proposed a carbon-based anode that could get away from these problems. And that led in 1991 to the first commercial lithium-ion battery commercialized by Sony. I don't have to watch the chat, Olivier, right? If there is anything serious, you tell me.
Okay. That's fine. I'm remodifying the question.
Okay. Good. No, I'm not moving. So what is a lithium-ion battery? Well, it is a device where you have anode and cathode, and in the discharge process, you have lithium ions released from the anode material to the cathode material. And at the cathode, you have this oxidation relation here where cobalt oxide is transformed into the layered lithium cobalt oxygen of good enough. And at the anode, you have the corresponding process. The reverse is happening when you put a voltage and induce the charging process. So discharge is a spontaneous redox reaction, and then the charging process leads to the inverse processes. Okay, required specifications, and this is really only a very, very partial list of what battery experts tell you. The required specifications of an ideal cathode material should be that it should possess an open framework structure, be of course a source of lithium plus and of a lot of lithium plus as much as possible. We will come back to this later. To be of high voltage to ensure high density of the energy, high energy density, sorry, to have the fast kinetics of the lithium diffusion. And of course, it should also be cheap, easily available chemical elements and environmentally as innocent as possible, thermally stable, chemically stable. And if now you go to the materials, so the time-honored example is the lithium cobaltate. Trials were done on lithium nicolates, but which were more or less discarded due to thermal safety issues. Then the runner is nowadays the NMC or NCA here, namely compounds where you have in the place of the transition metal, in the place of the cobalt, several options, nickel, cobalt, aluminium, or here nickel, cobalt, manganese. And this is indeed nowadays the most common cathode material for portable electronics. Cobalt-free alternatives have also been explored. People want to get away from cobalt for obvious reasons because of the mining issues. And one candidate is to put manganese here, which is indeed used in electric vehicles, but has lower energy density. And then there is research going on in various polyanion material combinations, and of course also on the anode side, also on nanostructuring, and many things behind these dots. Recent developments include studies of what people like to call lithium-rich oxides. An example is this one here, lithium 1.2, nickel 0.2, manganese 0.6, O2. And if you calculate quickly, you realize that nickel 0.2, manganese 0.6 does not sum up to 1. So the missing 0.2 is somehow on the lithium side here, which means that actually some of the lithium goes in the transition metal sites in this compound. And this is why we call this lithium rich. That holds currently the record for specific energy. And that is thanks to precisely this issue that the lithium being on the transition metal site, the charge compensation is done by the ligand, and that means that the oxygen ligands here take part in the electrochemical processes, and in particular into the redox activity, which is a means to enhance the capacity of your battery material. So what is this process that chemists call anionic redox? Well, it's a reversible redox process that involves the ligands and that leads to extra capacity. This type of anionic redox has been demonstrated in these lithium-rich oxides that I cited before, but proved to have unfavorable cycling properties, so some problems of voltage fade, for example. Anionic redox is generally favored if you increase, of course, the ligand content. So if you lower the transition metal to ligand content ratio. So for example, if instead of having 2 oxygens for one manganese here, you have lithium 2 manganese O3. And anionic redox indeed has a history in the chemistry community. It has been explored by Jean Roussel in France in the later 90s in sulfides, and in particular in these titanium sulfides here, where the titanium S3, the titanium persulfide, was thought of as a titanium 4+ ion, and then a sulfur 2- ion and a peroxy disulfur, which that wouldn't have 2- for 2 of the sulfurs. So eventually you take away electrons from the sulfur p shell. In a physicist's language, this implies, of course, that you are in fact dealing with a charge transfer material where you have the ligand states close to the Fermi level, and you can take electrons from the top valence band formed by these ligand states. However, the chemist's intuition here involves also that you have this excess of the lithium inducing this process. Okay, why is anionic redox interesting? Well, you have already seen if you can get more lithium out of your battery, you can enhance the capacity. And there is a kind of trade-off between the voltage and the specific capacity here. In the end, what is interesting is the area under this curve, because voltage times capacity gives you the energy density of your material. And that means you would like to enhance both the voltage and the lithium content, the specific capacity. The more lithium you can take out, the more capacity you have. If you can, by the tricks of the anionic redox, extend the area to this side here, even if you have somewhat lower voltage, you might still be favorable in terms of energy density. Okay, going back to the list of materials that I've shown you. Well, as people here on Zoom for quantum materials, correlated materials, what of course we are all striking with is that any of these materials involve partially filled transition metal shells. And that means when you want to do electronic structure calculation for those, you need to take specific care to include the correlation effects. So the methodologies that I think you are all more or less comfortable with include, of course, the basic density functional theory, but then also density functional theory plus Hubbard-U corrections and methods beyond that, namely density functional theory combined with dynamical mean field theory. So in the following, I will show you DFT calculations within the generalized gradient approximation in the flavor due to Perdue, Berker, and Ansoffer, and the PPE, and GGA plus U calculations, and then GGA plus DMFT in GGA plus U charge self-consistent flavor. Well, why is that? We will be treating quite complex unit cells, and full charge self-consistency with a full quantum Monte Carlo impurity solver at each step becomes expensive. Well, that is why with GeonSim we explored to do calculations where you self-consist at the GGA plus U level, you average over the spin, and you take the resulting density as a starting point for the construction of your Hamiltonian for the DMFT, so that it's in fact a scheme that you can view as iterating at a started mean field level and only at the last iteration using a full-fledged quantum Monte Carlo DMFT solver to solve the DMFT equations. We do that with a spin-independent, fully localized limit double counting and with a standard parameterization of the interaction vertex in terms of Slater-Kanamori parameterization for the 3D orbitals. Okay. Previous work on battery compounds is numerous, using DFT, DFT plus U, and even DMFT. And many people in the audience, I'm aware of this, have put a lot of sweat and work into these issues. So I will not give full credit to all the works done. That's just too much. My poor excuse is that I will not go to the lithium cobaltates nor to the lithium iron phosphates, but to one that I think you have not worked on, namely lithium 1.33 minus 2y over 3, titanium 2/3 minus y over 3, iron y, sulfur 2, with y determining the iron content of 1/3. So this is what I will dub in the following LTFSX, so lithium, titanium, iron, sulfur X, with X either being 0 for the lithium poor charged material, or for X equal to 1 for the lithium rich discharged compound. And that is, as you can guess already, a layered compound. The structure is here, where you have a triangular lattice structure in the typical transition metal dichalcogenide structure piled up, but with the sites here shared between not only titanium and iron, but also some of the lithium. And the Y here will adapt how much iron, titanium, lithium we will be having here. Okay, so my further outline is I first will have to tell you what is now special about this compound. Why do we take these phone numbers? Then I will discuss the electronic structure of the end members for lithium-rich and lithium-poor compositions X equal 1 and X equal 0. I will do that at the special point of Y equal 1/3 for the iron compound for reasons that I will discuss. I will discuss the role of Hund's exchange for the physics and conclude a little bit. Okay, so why this phone number compound here? Well, you may have realized that if I take out the iron, so Y equals 0, and I do a little bit of algebra here, my lithium 4/3, titanium 2/3 sulfur 2 is actually nothing else than the isostructural analog of lithium 2 manganese O3 that we have seen before in the lithium-rich oxides. So we are heading, of course, here again for this question of the anionic redox, except that now we have replaced the oxygen by sulfur. Sulfur is less electronegative, so the ligand states move closer to the Fermi level, and that means the anionic redox process should become easier. However, in the pure compound here, the lithium 2 titanium S3, titanium is in the 4+ configuration, and the whole thing is actually electrochemically inactive. So the idea of introducing now the iron into the compound can be thought of as taking the lithium 2 titanium S3, where you replace some of the titaniums, titanium 4+, by iron 2+, and then you adjust the charge by just adjusting the lithium content of the material. So this is what is actually happening when you do these phone number compounds. You add a little bit of iron, and then you do it by adjusting here. And that indeed induces now low energy states close to the Fermi level, which can be expected to be of iron 3D and sulfur 3p character. And that gives us a model system for the ionic redox that the chemists are interested in. So in a schematic picture, when you start from an oxide, one of the classical ones here, the lithium manganese oxide, and you move to the sulfides, overall you shift closer to the Fermi level. You have in the first place the empty titanium shell here. And then by adding the iron, you have iron states. So this is just a band structure picture, no correlations yet. You have iron D states here at the Fermi level together with sulfur non-bonding states at the top of the valence band. Note that here everything is drawn with a reference to a lithium plus anode and not with respect to the Fermi level, which of course would be somewhere then here. Okay, so what happens experimentally? Well, this phone number compound has been synthesized indeed for different iron contents. And here is the experimental result for the capacity as a function of the iron content, so of the Y. And that gives the curves that goes like this here. You see my mouse, right? Yes. So you see that the initially non-electrochemically active iron-free lithium titanium sulfide becomes indeed rapidly activated and then essentially goes via a maximum to a line which would be the theoretical capacity if you can take out all the lithium that you have. So you come close to that for some values, and in particular for the value of Y equal 0.3, which is close to the 1/3 that we will use later on precisely for that reason. Note also that interestingly what is drawn here is the theoretical capacity that you would have if you were only doing redox processes between iron 2+ and iron 3+, which are believed chemically to be the ones happening. If you were also dealing with iron 2+ going all the way to iron 4+, which chemists believe for good reasons not to be the case, then you could enhance the capacity, but not to the value that you have here. So that means this area is already indeed showing that you are doing anionic redox in this compound. So experimentally, we can note the remarkably high capacity, 250 here for this Y.3, 250 ampere hours per kilogram. And in this state, most power experiments show that you indeed, as I mentioned, fully reversibly oxidize between iron 2+ and 3+. And also that you have iron 2+ states in a high spin configuration. On the positive sides, the good news for the chemists is that now you indeed have better cycling properties, so you fix some of the problems that were seen in the oxides. However, this comes at the price of a lower voltage, because of course, with the states being closer to the Fermi level, that also means that you have voltages rather of the order of 2.5 electron volt instead of 4. Okay, so now let's switch to calculations. So this is just a plain vanilla GGA calculations, generalized gradient approximation calculations, for the two end members. So the one that I call x=0 and the x=1 compound here. Overall, you see the big chunk of sulfur states here in green in both plots. You have the iron D states and the titanium in orange. You confirm that the titanium here are empty. You see that the iron D, interestingly here, in the fully lithiated compound are gapped. And that is actually just the splitting between the filled T2G manifold, which has now 6 electrons, and the empty EG states here. In the delithiated compound, you have a D5 nominal configuration on the irons, and that means necessarily you go back to a metallic state. You have a T2G5 low spin and thus not completely filled T2G shell. Also plotted are in red here the sulfur p states associated to octahedra, where the central ion is not a transition metal but a lithium. So those are the ones that the chemists are interested in because of their non-bonding character. And you see that indeed there are quite a few of them at the top of the valence here in the lithiated compound. Okay, let me summarize a bit schematically what we have seen here. So we confirm empty titanium shell, the sulfur down here, but reaching up to the Fermi level in the delithiated compound, and the low spin configuration here, and a little bit larger splitting here. Okay, now switching it, you can see it better. And I give you additional information that the T2G EG splitting is indeed smaller in the fully lithiated compound than in the delithiated one. 1 electron volt compared to 1.8 nearly, so quite large splitting. Okay, from the electron counting, you also arrive at the nominal configuration of the sulfur, which is missing here 1/3 of an electron. So having empty states close to the Fermi level here. And that is, of course, already the sign of the anionic redox. Okay, now we can do this a little bit more in a more refined fashion. The upper panel is still the GGA. Spin polarized GGA actually undoes what we just achieved, namely the low spin band insulating lithiated compound here now becomes metallic again because you push electrons into the EG states. GGA plus U opens the gap again. however, has a depletion also here in the dilithiated compound. Moreover, this is not noted, if you look at the magnetic moments, the dilithiated compound has a magnetic moment of 2.3 μ-Bohr, which is not compatible with the experimentally observed low spin configuration in that compound. Overall, of course, we know that GGA plus U in this case will probably underestimate fluctuations, so we want to go beyond and to see what actually DMFT is giving us. This is GGA plus DMFT, again for the lithiated and the dilithiated compounds. And now you see that actually, interestingly, we reopen the gap here in the lithiated compound, and we found a mod insulator with a high spin configuration. However, in the, so this is for the D6 configuration, however, in the D5 configuration here, we rather have a peak at the Fermi level. And note that this is a peak both in the iron density or spectral function and also the sulfur states here again. So you see a strong covalency in both compounds, but even stronger actually in the dilithiated metallic compound. So we switch actually when we do the redox process from a high spin mod insulator to a low spin metallic system. This is the redox transition. So now we can look what we really gained compared to LDA plus U. So what are the fluctuations doing that we have added here in the DMFT? Well, solving DMFT equations with quantum Monte Carlo has the advantage that you can directly do fluctuation statistics. I think Thomas will come back to this much more in detail. So what we draw here is just the probability of visiting configurations with a given quantum number. And in the upper row, this is for the spin component, and in the lower panel, just for the number of electrons on the iron 3D shell. And again, left-hand side for the lithiated, for the lithium-rich compound, and right-hand side for the poor compound. And what you indeed see here is the peak. So just focus on the blue curves, which is for the, let's say, realistic Hund's coupling value. You have here a peak around, indeed, a value which can correspond to the high spin configuration. Whereas in the dilithiated compound, the distribution is really broad. Different configurations all contribute more or less equally. Also in the electron numbers, you have relatively narrow contribution here, but in the dilithiated compound, you have substantial contributions, even here from quite low and quite high electron numbers on the D shell. Okay, having said that we are treating with a metallic compound for the lithium poor version, we can of course also now investigate the properties of this metal from the point of view of a DMFT person of a correlated metallic system. And in particular, what we have looked at here is the quasi-particle residue. So the weight of the quasi-particles in the metallic state here as a function of the value of the Hund's coupling. And what we find is that the value for J equals 0 would be here about 0.7 something or 0.9, depending if you look at the T2G orbitals or the EG orbitals. But when you switch on finite Hund's coupling, this value drastically decreases, depends much more on the Hund's coupling than on the U. Dashed lines and solid lines are for difference U, and goes actually to relatively low values, in particular for the more occupied T2G orbitals here. So that means that actually for realistic values of J, which are rather around here than here, the quasi-particle residue becomes as small as 0.2 something. And that means that we are indeed in a quite strongly correlated metallic regime. But again, driven by the Hund's coupling J. So what in the literature people like to call Hund's metal. We have then
Okay.
calculated, yes?
5 minutes.
Yes, I'm quickly done. Thanks.
Okay, thanks.
We have calculated the temperature dependence of the spectral function, which shows the expected just broadening and without Hubbard bands corresponding to the scenario of the Hund's metal. Okay, then finally, we have calculated the voltage. So the voltage can be obtained just by a combination of the total energies of a delithiated and lithiated compound and the pure lithium. And so what is given here now is the GGL value, spin polarized GGA, and as a function of, again, Hund's coupling, the voltage in GGA plus DMFT. So in GGA plus DMFT, again, we have a strong dependence on the Hund's coupling. We approach the experimental value, which is somehow, as I mentioned, just below 2.5, so 2.48 something, which is nearly reached for the relatively large values of J. But what is even more interesting is the comparison of the shape of this curve, voltage as a function of Hund's coupling, with what you would get at the atomic limit. So if we calculate that thing, just energetics in the atomic limit and extract the voltage, we get actually a shape which is very similar, a kind of V shape with a flattish slope here and a more steep increase here. And that is essentially given by energetic balance between the crystal field splitting and the Hund's coupling, of course, which determines this thing. Okay, so last remark still. Now we have desiccated where the J dependence of the voltage comes from. And since we are dealing just with total energies here, we can, of course, look if this comes from the kinetic energy part or from the Coulomb energy contribution to the total energy. And the two voltages, so the contributions of the two parts to the voltage, are drawn here separately. In orange, the kinetic energy contribution to the voltage, and in blue, the potential one. And what you can see from that is that indeed the dependence stems more from the potential energy, from the Coulomb part to the total energy. And in particular, the increase here is, of course, as anticipated here already, due to the Coulomb interaction and in particular the Hund's coupling. Okay, with this I conclude. So cathode materials for battery applications are correlated electron materials, but with potentially quite complex unit cells. So in this case, we applied here GGA plus DMFT scheme, where we cheated on the charge self-consistency by helping us with the GGA plus U method just to iterate on the density. And then the application to the lithium-rich sulfides, the LTFS0 and 1, yield respectively a high-spin mod insulator and a low-spin correlated metal. That means the redox-driven spin state transition coincides with the mod transition. So overall, Hund's coupling determines the energetics of the compound, the physics of this compound, including the voltage. And okay, I have not insisted on that too much. The strong iron-sulfur covalency is crucial. We actually did analogous calculations just for the oxides. And in that case, you would have both materials, both end members, in large spin states with large moments. So one can conclude that both the choice of the anion the choice of the anion is essential actually for optimizing the battery properties such as capacity, but also operating voltage, of course. And finally, that means that battery materials are an intriguing and maybe important playground for correlated electron physics, and that in turn, also electronic structure tools nowadays can maybe be put at the service of the energy transition. Thank you very much for your attention.
Thank you very much, Silke, for the nice talk. So we are now good for questions. I think Antoine has a question. If
yes.
can hear you now. Yes. Okay.
Yeah. Can you hear me now?
Yes,
First, I'd like to wish a Happy New Year and a good start for this symposium to everybody. Previously, I was cut off from video and sound, so I couldn't do this in person. And thank you very much, Silke, for this beautiful talk, also pushing the boundary of applicability of DMFT. I actually have a question. So you emphasized both the importance of anionic redox, meaning the contribution of the ligands to the capacity, and the importance of the Hund coupling, which promotes the high spin configuration. But is there a logical connection between the two? Namely, is increasing the Hund coupling also, or modifying the Hund coupling also affecting the degree of ligand redox? Or somehow these are disconnected aspects?
Okay, that's a difficult question. It's an overall plot because, of course, if I go back here, the question of the strong hybridization is what enters here in the energetic positions of the states. So you have in particular here, for example, the large spin splitting, which eventually avoids the high spin configuration here. And then the second question of the position of the sulfur. So they are connected, I would say, okay, they are connected in the sense that the strong covalency, that the sulfur introduces two things: the strong covalency because of the extension, and also the relatively high position. So it's hard to have one without the other, but I wouldn't say that it immediately helps.
And perhaps as a footnote to my question, so you emphasize that in the metallic state, right, which is the lithium poor state, the histograms of states is very broad over different charge states. But is it such that within each charge state, it is still the high spin configuration that dominates? So that would qualify this state to be called a Hund metal?
No. It is in the metallic state, rather the low spin configuration. So.
Aha, I see. So if we look at within each n, value of n, right, we can decompose, we can make histogram for separate multiplets. You are saying it is not the high spin multiplet in each charge configuration that dominates?
No. But nevertheless, you have the phenomenology of this here. So it is in that sense that we say Hund's metal. It's not in the sense of really having high spin configuration. Yeah.
Okay, thank you. Thank you.
Okay. For some reason, Andy would like to ask a question, but he cannot technically. So yes, given the question to me, so I'm going to read the question. I understand that an important figure of merit is the speed of charge and discharge. Does the many body electronic structure appear on this issue?
Oh yes, that is one of the questions, Andy, sorry, that I avoided, because I am not sure that I can say anything intelligent on this. So indeed, you're right. This is one thing that the chemists are very concerned with. But at this stage, we do not have any theoretical input on the kinetics.
Okay, thanks. So on the actually two questions, I'm reading this next, and then we take the next question. I understand that stability over many cycles is an important issue. Okay, that's the many body electronic structure there on this issue. So stability over many cycles.
Yes, somewhat more, I would think, because the stability over many cycles goes along with the energy barriers of close compounds. So, for example, if you have in the oxides, for example, in some cases, you have oxygen gas being freed or something like that. And that is, of course, a thing that in principle can be assessed by the energetics and the calculations of the kind that you can do here. We didn't do that, but I think this is more
okay
in reach.
Thanks. So Next question, Carsten, you had a question?
Yeah, thank you, Olivier, and very inspiring talk, Silke. Very nice topic. So I wonder about the Hun's exchange. So you said it's 0.9. So sometimes you have something like 0.9 or 1 if you have a density kind of Hun's exchange, but it's somewhat lower, 10 or 20% if you take the full SU2 symmetry into account, because the singlet and triplet splitting is larger in the SU2 form. So is this 0.9 including this effect, or is it the RPA value from a density kind of DFT calculation?
Here we are doing density interactions.
Mm-hmm. Okay.
I should have noted that. So whenever we did not calculate the evolution as a function of J, we fixed 0.9 as the value that you would believe to be the realistic one.
Okay, so in this framework, it's the right value. Okay.
Interestingly, one could speculate, because the calculated voltage would even suggest here that indeed it has to be at least 0.9. But maybe there are, of course, also other effects. So it has to be a large Hund's coupling.
Okay, yeah, thanks.
Thanks.
And Happy New Year.
Thanks, same for you.
Michel? Michel, quickly.
Yes.
For the last question, because
can you hear me?
Yes.
Yes.
Hello.
Thank you. Yes. Thanks a lot for the very inspiring calculation on this important materials. So in the beginning, you mentioned that what makes this material special is that you're starting to oxide the sulfur orbitals. But your DMFT only included like the d orbitals of the iron site. So where in your calculation do you see this contribution from the sulfur orbital coming into play?
Yes. No, we do put a self energy only on the iron orbitals, but we have the full states, including sulfur, iron D, titanium, in the calculation. So that means, and in particular, of course, also already at the initial stage, when we prepare the Hamiltonian for the final iteration from the GGA plus U, there you have also charge transfers between different.
So it's when you build your localized orbitals that this is where the mixing is coming in?
Yes, yes, absolutely. So you have a Hamiltonian which has everything in. It's just that the self-energy applies only to the R&D states.
Okay, so it's that the GGA plus U part that you see this mixing coming into play.
Already, yes, yes. But also later, I mean, when you look in the DMFT, for example, if you see a spectral function like that here, you understand that here, indeed, you have states which are actually sulfur iron hybridizing.
Okay. Yeah.
So this is independent from the fact that I treat only the irons as correlated. The others are there.
Yeah, they're there. Okay. Thank you.
Yeah.
Thank you.
We have time for one last quick question by Rialul.
Yeah, do you hear me?
Yes.
Yes.
Bonjour, Henri.
Yes. Bonjour. Okay, I just have a simple question. When you did calculations for two compositions, in these compositions the unit cell was well defined, or did you have to do fractional occupancies?
Now, in this composition, the unit cell is luckily well defined, and that's why we did actually two.
Yeah, okay.
We had the experimental lattice parameters, but then we had to optimize or to find the internal positions. But the ratios were the lucky ones that we chose like that.
Okay. It would be difficult to do your 1/3 filling, for instance.
Yes, yes.
Yeah. You see
right.
why I'm asking that,
Sorry.
because I'm thinking to cobalt it. It's okay, but
Well, we can
if I have time, I'll drop at École Polytechnique and discuss with you about that. Okay.
With pleasure.
All right. Thank you very much. Antoine, you wanted to say?
Yeah, I
something?
just want to make a very
Conclude?
quick comment, perhaps to clarify the question, also the discussion that Michel Coté started. So Silke, just to make sure I understand. So the calculation is done using all states, right? Including the ligand states and everything. And so you use what we call a big window, right?
Yes, absolutely.
And self-energy is only put through the MFT on the D states. So it's not only through the choice of the Vanier functions and so on that the hybridization with ligand is actually taken into account. It's through the whole charge redistribution between ligand and transition metal, since you do handle the full big window electronic structure, right?
Absolutely, yes.
Yeah, wanted to clarify that.
That's what I tried to say, yes.
Thank you very
Sorry for
much.
repeating.
Thank you all, and thank you, Silke, for the very nice talk. We now have to move to
Thank you.
the second talk.